Hello, this is Raj Patel here, and today we're going to be continuing talking about circuits. Last week we talked about uh, circuits, Kirchhoff's two rules, the loop rule and a joint rule, and we also talked about series versus parallel circuits. And so now we're going to solve some more circuit problems, talk about power and charge. And so first we're going to solve this circuit problem here. And so here we have a resistor which is 30 ohms, and then a 20 ohms resistor and a 50 ohm resistor, which are both in parallel. And so let's first collapse down the parallel component. And I like to say parallel is with these two I's, capital I's, because they're two parallel lines. So we're going to collapse down the parallel component into an equivalent resistor. And the formula for equivalent resistor with two resistors in parallel is 1 over Req, so 1 over equivalent resistance, equals the sum of the reciprocal of all the resistances. So 1 over Req equals 1 over 20 plus 1 over 50. And so if we cross multiply, so by cross multiply I mean multiply 20 across to this one, 50 across to this one, and then we multiply 20 and 50 together. And so it should look something like this. So 20 on top, because 20 times 1 is 20, 50 on top, 50 times 1 is 50, and then we put those on the top and add them together, and then we multiply 20 and 50 together. So this is what I mean by cross multiply, and this method will always give you the answer. You don't have to worry about common denominators or anything. This will always work. And equals 1 over Req, so we flip both sides of the fraction. And so we get Req equals 1000, which is 20 times 50, and then over 1000 over 70. And if you divide that out, you'll get 14.3 ohms. So now that we collapsed it down into this one resistor here, we have two resistors. So now we can add these two both together and collapse it down to one resistor. Um, so this rule for a series, it's pretty easy because the equivalent resistance is just the sum of all the individual resistances. So the reason why it's series is because there's only one path for the electricity to travel. There's no choice for the electricity to make like in the parallel one. So this is series, so we just collapse it down to one resistor like this. And so we add 30 and 14.3 because that's our new equivalent resistance. And we get 44.3 ohms. So now we're going to solve for the total current. Now that we have our simple circuit here, we only have voltage, resistance, and then we have current, which we have to solve for. So since we know V equals IR, so the total voltage equals the current times the equivalent resistance, which is 44.3 in this case. So if we move the R and divide both sides by R, we will get the current. So we basically substitute 12 volts is the total voltage, 44.3 is the equivalent resistance of all of the resistors together, and we get a current of 0.27 amps. So now we want to figure out the voltage drop across the 30 ohm resistor. And so here is our original circuit. So now we got to bring it back, and we want to find out the voltage drop across the 30 ohm resistor. And so basically every time the current goes through a resistor, the voltage drops. So think about if you have a river flowing and you have a water wheel. When the water goes through the water wheel, it slows down the current of the stream, but but there's still the same amount of water leaving as that entered. So that's what a resistor does. It just takes away voltage or the potential of the the stream or the flow of current. So the voltage drop across 30 ohm resistor is V equals IR. So the current is 0.27 amps. The resistance is 30 ohms. So we get a voltage drop of 8.1 volts, which is pretty much most of the voltage drops at that one resistor. So that's quite a bit of the voltage. That's about 66%. And so now if we use the loop rule, we know that in a loop, the voltage equals 0, and if we made the loop clockwise in this case, and the current we know is clockwise, batteries are positive, resistors are negative, and if you are not sure why that's true, just look at the last video I made. We talk about the loop rule, so if you want more practice with that. So, so basically the voltage of the battery minus the voltage of this resistor and the parallel component, because we know that parallel components have equivalent voltages, equals 0. And so then if we move uh, this side or parallel to the other side and we plug in what we have here, we'll get voltage of the parallel equals voltage of the battery minus the 30 ohm resistor. And we basically get 12 minus 8.1, and it gives us 3.9 volts. So that's the voltage across the parallel component. And like I said before, voltage across parallel components is the same. So now we're going to solve for the current in the branches. So V equals IR. So to find current, we just do voltage divided by resistance. So so the current in the 20 ohm resistor is V of the voltage of the parallel divided by 20 ohms. And in the 50 ohm resistor, it's voltage of the parallel divided by 50. So now we do 3.9 divided by 20 gives you 0.95 amps. 0.39 divided by 50 ohms gives you 0.078 amps. And so those are the two currents of the individual resistors. So so that is the answer, and basically we've solved the whole circuit. And this is important that this obeys the joint rule, Kirchhoff's, junction rule, junction rule, I should say, because, um, because the two amperages, when they're added together, it equals the total current. And if you remember back from here, the total current was 0.27 amps, and when we did the problem, we got 0.273 amps, which is comparable, but depends on the rounding, how much you round. So, but it does definitely obeys the junction rule. Another method, instead of doing V divided by R for both, is you could have found the current of one of the resistors in parallel and then subtracted that from the total current, and that would work perfectly fine. And here's an important, cool pattern that we noticed, or that is true about circuits or resistors in parallel, is that the ratio of the resistance of one of the resistors out of the combined resistance times the current equals the current of the opposite resistor. So let me just show you. That sounds very complicated, but it's not that hard to see. So basically, let's just say we're looking at the 50 ohm resistor here. So 50 ohms, so the resistance of the 50 ohms resistor out of the combined resistance of both of them together times the total current gives you the current in the opposite resistor, which would be the 20 ohms. So this is what it means. So if we're looking at the 50 ohms, its resistance is 50. The combined resistance 20 plus 50 is 70. So combined resistance just means the sum of the two. No equivalent resistance, nothing like that. Then if we multiply that by the current, we know the total current was 0.27 because we solved for it when we collapsed down the circuits. This gives you the current for the 20 ohm resistor. And then if we do the same for the other one, 20 over 70, so 20 ohms, because it's this resistor, out of 70, which is the combined 20 plus 50, and then we multiply that by the total current, we will get the amperage of the other resistor. And notice it's the same exact thing as above. So this is true um, because remember, the higher the resistance is, the less of the current they get. So if they were equal, so let's just say they're both 35, the current would be split equally between the two. But since they're since they're different, if it has greater resistance, it'll get less of the electricity. So that's why it's the opposite. So that's why the resistor you're looking at, its current over the combined times the current gives you the opposite resistor's amount. So this is a kind of cool method you can use to solve for current. So now we're going to have another problem, but this is not the traditional collapse down all the circuits and find the current. This time, I'm going to give you the current and some of the resistances, but you will have to solve for one of the ones in parallel. So we can't solve for the combined resistance, but we need to figure out the voltage drop across the 10 ohm resistor. So let's figure out the voltage drop across the 10 ohm resistor. So V equals IR, so it's already given. We just multiply the current and resistance. So the current is 0.5, I give that to you. And the resistance of the 10 ohm resistor is obviously 10, which I just told you. So that gives you 5 volts. And so if we say the battery is 9 volts, sorry, I forgot to label that on my diagram, but the battery's a 9-volt battery. So using the loop rule, Kirchhoff's loop rule, 0 equals the voltage of the battery minus the voltage of this resistor here, minus the voltage of the parallel component here. So if we move parallel to the other side, voltage of battery minus the voltage of the 10 ohm resistor equals voltage of parallel. So 9 minus 5 equals 4. So the voltage across the parallel component is 4 volts. So now that's all and good, but what are we going to do with the 4 volts? So the best way, or the way to solve it, is to use the 4 volts and to find out the current in each branch. Each of the 2 or the 20 ohm branch, and then you can find the other branch, the current in the other branch, and then you can find the resistance. So the current in the 20 ohm resistor is V over R, because V equals IR, so if you divide both sides by R, V over R equals current. So the voltage of the parallel component was 4, the resistance was 20, so 4 over 20 is 0.2. So that's the current in the 20 ohm resistor, so 0.2 amps. Now the junction rule, sorry about the joint rule, it's the junction rule, is uh, the current in 2 branches has to equal the original current coming in. So the sum of the 2 branches must equal the current that came in, because if you have a hose and it splits up into 2 tubes, the water coming into the 2 tubes should equal the water leaving the 2 tubes together, because none of the water should be disappearing into like a black hole or something like that. It should be equal. So that's what the junction rule says. So basically the current, so 0.2 plus the current in the unknown resistor must equal 0.5, because 0.5 was the total, 0.2 is taken from the other side. The other one needs to have some current. So it turns out to be 0.3. And so now that we know the current, and we know we know the voltage across the parallel component, we can solve for the resistance. So V equals IR. To solve for resistance, you do divide both sides by I. So V over I equals the resistance. So the voltage of the parallel divided by the current of the unknown R equals the 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 resistance. Sorry. So 4 divided by zero point 0.3 equals 13.3 ohms. So that is the unknown resistance. So now we're going to do a horsepower problem or a power problem. So, so a motor with a 24 volt power source and a 360 ohm resistance can lift the the 5 kilogram block how far if it's left on for 1 minute? If power equals a current times voltage, so P equals IV. So that's your formula. So um, so first we want to find the current because in our power formula it's P equals IV. There's no resistance. So we need to find current. So V equals IR. So current is divide both sides by R. So voltage divided by resistance. So if we do that, 24 volts divided by 360 ohms gives you 0.0667 amps. So that's our current. Now that we have current, we have voltage, we can figure out power. So 24 times 0.0667 gives us 1.42 watts. And if you remember back from energy, watts is joules per second. So keep that in mind. And so if we want to find out how many joules are used in a minute, we have to convert. And so joules per second. So this is per second, and we want a minute. So a minute is 60 seconds, so we multiply 1.42 times 60 and get the total amount of work or energy we have, which is 85.2 joules. And this is all from energy, so you can take a look at my videos on energy to get a review about this. So remember, work is the change in energy, and since we're lifting a block, let's just assume the block is moving so slow it has no kinetic energy, so it's only gravitational potential. So work is change in energy, which is mgh if we're only using gravitational potential. So to solve for the height, we divide both sides by mg. So W, work, divided by mg equals height. 85.2 divided by 5 times 10 because it weighs 5 kilograms. And gravity is 10 meters per second squared. So 85 divided by 50 gives us 1.7 meters approximately. So this motor can lift this block 1.7 meters in 1 minute. So more about power. Power is the rate at which work is done, so joules per second. Same thing with energy, it's the same unit, joules per second. And power is how circuits are related to the real world. So, within like when you're just talking about circuits, all you can do is pretty much solve for current, resistance, or voltage. You can't really do much outside that. But with power, you can solve for how much work it could do, how much heat is dissipated. So a good problem is like you can talk about the heat dissipation of a bulb, which would be a good thermodynamics problem, but we don't do that in my AP1 class, so that would be an AP2 thing if you're planning on taking that, or if you're taking physics and your teacher wants to do thermodynamics, that would be a good problem you can talk about. So now that I told you P equals IV, there are other ways power uh, is there are other formulas for power. So since we know V equals IR, power can so we can substitute the V for IR. So P equals I times IR. So power could equal current squared times resistance. So this is another way you can solve for power. So we didn't really need to replace it, but I just gave you the basic formula, the most common one. And then now we have P equals IV, but current is voltage divided by resistance because we just divide both sides by resistance. And so power can also be V over R times V because we substitute the current. So it's V squared over R. So power is either P equals IV, P equals I squared R, or P equals V squared over R. So there are several ways you can solve for power. So last thing I have to talk about is charge. And so charge is basically caused, or charge is Q, is caused by an unbalance in electrons and protons. So whenever something loses an electron or proton or something, it has a charge. And so charge, there's three types of materials you need to know: conductors, insulators, and semiconductors. So conductors, charge is free to move throughout the material. And then insulators, charge is stationary. So often, like balloons, if you rub your hair against a balloon, the charge will stay where the balloon touched your hair. So it'll stay in that area because a balloon is an insulator. And a cool thing is, if you take a balloon and hold it up to a very thin stream from your faucet, it'll actually make the water curve towards the balloon. So this is an interesting thing because water's polar, and so it actually moves towards a balloon's charge. So that's kind of a cool thing if you want to try it out. And so make sure the stream of water is very, very thin, like maybe a centimeter, like even like half a centimeter, a few millimeters thick. So very, very little stream. So that's a cool thing you can try out, showing an insulator, which is a balloon. And also semiconductors, charge moves with the resistance. So it lets like a little bit of it move, but not as much as a conductor. So remember, charge always, like just like magnets, wants to repel each other if they're all the same. So like, let's just say they're all positive charges, and if there's a wire, charge wants to move away from each other. So charge pretty much is always on the surface of any material. So if we have charge on a wire, charge will always want to be on the outside. So that's an interesting fact. Charge is on the outside of wires. And uh, charge in an insulator stays where it's deposited. So if you rub your hair against a balloon, the charge will stay where your hair touched it. And then if you hold it up to the water, that one point will be negative or positive depending on what it is. And it'll actually attract the water molecules. So that's kind of cool. So try that out. And then the last thing is Coulombic attractions. And pretty much this is the formula. So force of the attractions is K times Q1 Q2 over R squared. So similar to Newton's law of gravity. So this is very similar, but charge has K, which is electrical constant, and it has a 9, which equals 9 times 10 to the ninth, while gravity has while big G, or the gravitational constant of the universe, has only 6.67 times 10 to the negative 11th. So charge is much stronger than gravity. So in fact, pretty much gravity is the weakest force because you can beat gravity just by raising your hand. When you raise your hand, jump, walk, you're basically beating gravity because you fought it and got off the ground. But charge is much stronger than gravity because gravity has a constant of to the negative 11th, and then K has a charge of to the positive ninth. So that is much larger or much stronger. So charge, unlike gravity, can both attract and repel. So that's why the formula has a absolute value sign. So just like how if we talk about potential energy, but we substitute with gravity, we get this formula: negative gmm over r. Voltage is K times Q1 Q2 over R. So, and voltage is basically the desire for the electrons to move. So just like gravitational potential energy, when you substitute into gravitational potential energy with Newton's law, you'll get voltage equals this little thing right here, and voltage is a desire for pretty much electrons to move, and it's also sometimes called electromotive force, electron motive force. And the last thing is resistivity equals rho times L over capital A, where rho is the resistivity of the material. So how resistive is it? How much resistance it has. L is the length, so the length of a wire, let's just say. And A is cross-sectional area. So basically, if you took a slice out of it, and so if you took a slice out of a wire, how big is a circular part? And so resistivity, if we increase that, we have a greater resistance, obviously, because on the top of the fraction. If we increase the length of a wire, it has more resistance. So think about it. If you're running through tall grass and you're picking a path 100 meters or 2 meters, obviously the 100 meters is going to have more resistance because there's simply more of it to run through. So longer wires have more resistance than shorter wires. And A is cross-sectional area. So basically, how wide is the path? So if it's a wider path, it's less resistance. Because think about it, like if people are trying to squeeze through a door or a whole 10-foot section of a hole in a wall, obviously the door has way more resistance. So if we increase the cross-sectional area, we have less resistance. So basically, a longer resistive thin wire, or so longer resistive thinner wires have the greatest resistance, unlike shorter, fatter, and less resistive wires. So that is how resistivity works. So even on the AP exam, they might ask you one question, maybe tops on this, but it's always good to be prepared, especially for the AP Physics 1. But now you know about resistivity, Coulombic attractions, and solving circuits, pretty much. So thank you for watching Mirage's physics videos. So today we learned about solving circuit problems, power, charge, and resistivity. So that was a lot today. So congratulations. So you have finished pretty much all the material for AP Physics 1. So if you're in AP Physics 1, you pretty much finished all the material. And so keep on practicing for your exams, and especially for the AP exam, and then get that credit. Get a 3 or 4 or 5, and you'll get credit in college. So keep on practicing, and I hope you had fun learning about physics throughout the year. Um, Please, if you enjoyed this video, spread the word, tell your friends, and like this video. And this is more of like a review kind of videos. So maybe if you're studying for the AP exam, you can just watch some of these videos just to get a refresher on what is what, if you don't understand it. So email me any questions and comments at mpatelbuccaneer@gmail.com. I'll gladly answer. And for chemistry tutorials, please visit my website, buccaneerchemistry.weebly.com. And so thank you for listening to my videos throughout the year. And please tell your friends. I'll gladly like the support. And email me anything, physics related, maybe something cool or something I should make a video about, I'll gladly do it. And I hope to uh, learn more physics, and I might make more videos for like thermodynamics, more complicated circuits and stuff like that. So please, please email me any questions or anything. And thank you so much. It's been a pleasure, and have a great day. And I hope to see questions from you, and I hope to see you again on my videos. Thank you.